Okay, on to geometric optics. Geometrical, I guess, is not incorrect. I usually say geometric optics. We'll talk about two phenomena, refraction and reflection. Refraction is probably the more difficult, so let's begin with that. Refraction is a phenomena that is for waves. Waves bend around obstacles. You've seen it before, like if you have something out in the water and you have a wave that comes along, it'll just sort of go right around it, or it might even sort of bend around it. We see that with sound too, that if you stand behind a door or through an open doorway and you stand out of sight, you can yell and people still hear you. It's because the sound wave will bend around obstacles. It's not blocked like particles are. So this is purely a phenomena for waves. And it results because the waves travel at different speeds in different medium. So it'll travel at a different speed in a different medium. If a wave goes from one medium to another, from water to air, from hot water to cold water, then the wave will travel at a different speed. We describe this by something we call the index of refraction. N is the index of refraction. It describes how much the speed changes when it goes from one medium to another. And it's equal to c, which is the speed of light, divided by v, where here v is the speed in the medium. Remember we said that light has a constant speed when it's in a vacuum? That's that 3 times 10 to the 8th. Well, it slows down when it enters a medium. So here n is equal to the speed of light divided by v. For a vacuum, what does n equal to? Well, I know that in a vacuum the speed of light is c, and so if the speed in a vacuum is c, then n will equal to 1. For all other media, what is n going to be? Is it going to be bigger than 1, less than 1, or equal to 1? Well, if it slows down when it enters into a medium, then that would mean that v would be less than c. So v, if v is less than c, then that means that n is bigger than 1. As I said, c is the speed of light. We've seen that before. It has a value equal to 3 times 10 to the 8th meters per second. Traveling at different speeds as it goes to different media can cause the light to bend, or the wave to bend. So imagine that we have two media. Let's say that this is air. Air basically has the same index as a vacuum. It's not that much different. It's equal to 1. Actually, the index is like 1.0004 or something like that, but we'll just assume that it's equal to 1. And then it travels into, say, glass. And the index for most glass materials is about 1.5. That means that the speed of light in air is 3 times 10 to the 8th meters per second, same as a vacuum. Now I can calculate the speed of light in glass. N is equal to c divided by v. So v is equal to c divided by n, or 3 times 10 to the 8th. That's the speed of light, divided by 1.5. 3 divided by 1.5 is equal to 2, so that's 2 times 10 to the 8th meters per second. Make sure that you can do that sort of calculation for the test. I very much expect that you will have to do that you can use this definition of the index of refraction to calculate the speed of light in a medium, like glass, where it's equal to 2. You'll know, by the way, that it's always less than 3 times 10 to the 8th because light always travels slower in a medium. So let's imagine, I'm going to draw a line here. This is our normal line. It's called normal because it's perpendicular to the surface. Let's imagine that I have a light ray that comes in like this. That is the ray interpretation of light. But it really helps us when we're talking about refraction to think about the wave fronts. And so I'm going to imagine the wave fronts as they travel in. You can think of them like waves coming onto the shore of a lake. They're my wave fronts, and they all travel at the same speed. All points on the wavefront as it travels through this medium all travels at the same speed. So at every point along this wavefront, the light is traveling at the same speed until it gets here. And then I have one part of the wave that begins to enter into the glass. And because it enters into a point where it's traveling slower, the speed of the wave at this point is going to be slower than the speed of the wave over here. And so what that causes the light wave to do is that this part of the wave is going to come around faster. It's kind of like a bulldozer or a tank, if you've ever driven a tank, that in order to make it turn from one side to the other, you make one side of the tracks go faster than the other side of the tracks. Or if you've ever driven a dual propeller boat, a boat that has two propellers on the back, in order to turn the boat, you just make one propeller go faster than the other. And so that's what we're doing here. I have the light traveling faster on this side, and because it's traveling faster, this whole thing is going to rotate around until when it gets into this medium, it will have bent. So that is the bending of light that occurs in refraction. I can too, by the way, go from glass to air, although you can probably guess what's going to happen there. On this one, I talk about the light bending towards the normal. Remember, this is called the normal line. And this angle right here is now smaller than it was up here. So this is called bending towards the normal. Bend towards the normal. A right line there, that's assumed. That is bending towards the normal line. So what if I have my light ray over here? I imagine my wavefronts. Here, is it going to be traveling faster or slower as it encounters the air? Light travels faster in air, so it's going to bend the light in this direction. All right, so notice this light ray, since this angle is smaller than this angle, this bends away from the normal. Okay, the law of refraction. It's a mathematical formula. You're not going to have to use it, but in fact, no, I don't really. I'm just going to give it to you there, so you're not really going to encounter it. Okay. Pause.